Hey everybody, it's Mike here, and welcome back to my channel. We are coming back with some more vector calculus problems. This is in the vector calculus playlist, and specifically in this video, we're going to go over some more difficult vector problems. So hopefully to watch this video, you kind of have an idea of what vectors are, you know the gist of it, you know that they're directions that point to something in space, and you know how to write vectors in vector notation, right? So you've got x, y, z if you have 3 dimensions. Otherwise, they're just x, y. And you know what those brackets mean. You know what that means, that it's a vector, and you know you can draw them relatively accurately. So that's our starting point, okay? And now we're going to dive into some of the more nitty-gritty problems you might see. And so the purpose of this video is if you can do these problems, you're in a good place for this chapter. So this is following along with OpenStax, which is a free online calculus textbook, and we are going to be using volume 3, and this is from section 2.1. All the problems will be linked in the description below. So feel free to follow along in this video. Let's go ahead and start with the first problem here, problem 18, and it says let A be a standard position vector. Now that word standard is important, so I'm just going to highlight it. Let A be a standard position vector with terminal point at 2, 5. And it says let B be a vector with initial point -1, 3, and terminal point 1, 0. It says find the magnitude of the vector a minus 3b plus 4i plus 14 minus 14j. Don't let that confuse you. All they're asking here is, you know, here's a vector, and let's name this vector. I like to try and keep things organized. So we are going to call this big vector w, and w is going to be what all of this ends up being summed up to. So I'm going to give you about 30 seconds, or maybe just pause the video if you want to attempt this for yourself, and we'll come back in 5, 4, 3, 2, 1. Okay, so if you've attempted to solve, wonderful. If not, let's go ahead and follow through, and we'll show what we can do here. So it says, I highlighted that standard position vector word. I'm going to use yellow because I'm a little particular on my highlighter. I highlighted that word because it tells us something important. So what is a standard position vector? So as we know, a vector can be anywhere in space, right? So if I have a little graph right here, this is going to be a vector. I could take a terminal point and an end point and connect them with an arrow, and that is a vector. Now a standard position vector has one really simple property, and that is that it always starts right at the origin. So 0, 0. That's where it always starts. That's our initial point, right? And so that's why you may have noticed that A doesn't actually give you an initial point. And it's because we assume with any standard position vector, it's basically implied, it's implicit that the initial point is at 0, 0, just like that. And so we do actually have both points for that. And standard position vectors, it makes them really easy to name, because that means that with a standard position vector, you know, if our point is 0, 0, and we know that to find a vector, we take the initial point and we subtract we take the final point, we subtract the initial point. That means that we have 2 minus 0, 5 minus 0. So any standard position vector is always just going to be that endpoint. So 2, 5. Because to go from 0 to 2, 5, we would just go 1, 2, and then up y, 5. Right? So there's our standard position vector, and we're going to say that's A. And I'm going to try and keep these organized. So we're going to move A down here. There's A. Then we're going to do B. So it says B is a vector with initial point -1, 3. and a terminal point 1, 0. So let's think about how we would find B. And the biggest thing I can tell you, the biggest hint, is to remember, like if you've watched the last video that I've made, vectors are instruction sets, and they tell you how to go from one point to another point. And so you can graph this if you want. So just for fun, we're going to go ahead and do this graphically for a minute, and I'm going to go ahead and show you. Maybe that'll help you kind of visualize what we're doing here. So it says let B be a vector with initial point -1, so we're going to go -1, that's 1 in this direction, and 3, 1, 2, 3, so there's point, I like to call it point 0, and we can title this 1, 3, and terminal point 1, 0, so right there, P final, which means our vector is going to come down. And make sure we have the arrow pointing towards that end point. You never want the arrow pointing towards where you started, right? We're showing where we went, and we went this way. So here's our vector, and we can think about this as a direction set for a very specific reason. What we want to do is say, hey, I started at this point. How do I come down to this initial point? And let's do this bit by bit. So let's start with the x-axis here. And if I wanted to, and I like to think of the x-axis as this extended one-dimensional kind of line, right? And so if I wanted to be on the line x equals -1, that's this line right here, and I wanted to move to the line x equals 1, well, what do I need to do? How far in the x direction do I need to go? And the answer, of course, when you see it like this is 2. You go x equals -1, x equals 0, x equals 1, and now we have the x component of our final point satisfied. So the first part of our vector here, let's say b, is going to be 2, right? We move to 2 in the x direction. And let's do the same for the y direction. So in our y-axis, right, if we start from the line y is equal to 3 and we move down to y is equal to 0, well, to get from y3 to y0, we have to subtract 3 from our initial starting point. And so the y value of our vector is going to be -3. So, and just to clarify what we've done here, right, a nice little check you can do for yourself is plug in the original point and think about what happens with that vector. So if I start at -1, 3, we can do this purely numerically. If I start at -1, 3, and I use my vector as an instruction set, let's add 2, -1 plus 2, and let's subtract 3 from y. So -1 plus 2 is 1, and -3 minus -3, excuse me, is 0. And of course, that is our final point. So that means we worked, the vector is correct, and that instruction set gets us exactly where we want to go. That arrow is doing its job in space. So now we've discovered what A and B are. It says find the magnitude of this massive thing, this vector. We said we'll call this vector W for the sake of kind of organization. And W is comprised in, it looks like it's done in standard unit vector form, or standard basis vectors. And what that means is that we don't really know the x and y components here. I mean, we kind of do, right, because we have A and B and we know what those are. But the way W is given to us, it's not given to us in the traditional vector format A and B. But what we do have is something that means the exact same thing. So what we have here is some amount A, and then we're going to add 3 times, or subtract, excuse me, 3 times the quantity B. And then remember that I and J just refers to the x and y axis. So x is always I, and y is always J. And these are conventions you'll see a lot in upper level math classes and upper level physics classes. And we just like to have a standard way to talk about the vector quantity x and the vector quantity y without just using x and y. So it's just an evolution of the y-axis and x-axis language you've already been using. So don't let it freak you out. So 14i minus 14j, all that's saying is that we're adding 14 in the x direction and subtracting 14 in the y direction once we've figured out what a minus 3 and b are. So let's go ahead and do that, and the best way I like to do this is, like I said, I'm one for organization, so let's go ahead and do the vector 3b down here, and let's write this out. So whenever we have a scalar, right, and that's a scalar is a regular number. It scales a vector, and that's the nice way to think about it. So if we have a scalar quantity here, this 3, and we scale a vector, think of it like scaling the triangle from the last video. So what that means is that if our vector points here, and this is the hypotenuse of our imaginary triangle with an x and a y component, and I have h for the hypotenuse, which is also the length of the vector, and I multiply it by a scalar quantity like 3. You can do this with any triangle. Go test this. What you need to do is multiply each leg by that exact same number, which is 3 in this case. So the scalar scales the triangle just like this. And now this guy is equal to 3, and the side lengths happen to be the original side lengths times 3. So doing that, let's go ahead and show this here. If we have 3b, that's going to be equal to 3 times 2 and 3 times -3. See what we did there? We're scaling the legs of our little proverbial triangle, and that's going to be equal to 6, -9. There we go. And so that's the vector 3b. So I'm going to move this up. And now one thing I want to do here is notice that we've been using this arrow vector notation, which is nice. The little brackets are handy. I like them. I think they're clean. But the vector to us is given in terms of standard unit vectors. And so what might be better to do is to convert these into standard basis vector form. So let's go ahead and do that, and it's super simple. This shouldn't take you more than 30 seconds. All we're going to do is take the x. Remember that for any vector, we have x and y as our direction set. And maybe in 3 dimensions you'll have z. But what we'll do here is just substitute in the i's and remove the brackets. So 2i plus 5j, and this is the same vector. And all this is saying is this is a more direct direction set, because 2i plus 5j is saying we're going to go 1, 2 in the I direction. This is the first vector. And then we're going to go 5 in the j direction, which would be here. And that is our vector. So that it's super simple. Don't let it, confuse you too much or anything like that. It's very, very simple in what we're saying here. We're going to do b, and it's going to be the same to, I'm going to not highlight these because I think you get the point, plus, and now this is a negative 3, right? Negative 3j. So what would we say there? Well, we could simplify that to 2i minus 3j, because we're just going down in the y direction. And so that's how you can read this in your head. You can say over 2 in the I direction, which is x, and then down 2 in the y direction, which is j. Okay, so then 3b is going to be 6i minus 9j, and those are your standard vectors, standard unit vector form. So now that we have these, let's go ahead and compute w here. Let's compute this big vector. And so we will have a. And the reason we set this up like this is now we can kind of treat I and j like variables, just regular, normal variables that you're very accustomed to. So let's do that. So here's 2i. Try and make that I look a little less j-like. So 2i plus 5j, right? And that's a. So all I did was take a, and I've substituted a in for the first bit of this equation. So a goes here, and we're just writing out what we see up here, minus 3 times b, which we already calculated beforehand, so minus this guy. Let's use a different color too. I'm going to try and make this as clean as I can. So here's 3b, and we're going to be using this guy, so minus 6i minus 9i plus 14i minus 14j. Great, so now we've kind of set this up here, and just like any time we have two variables in one equation, we're going to do the same thing we've been doing for years now, and that is that we're just going to group them. So first of all, let's distribute this negative sign to kind of clean things up. So the negative sign here with positive 6i is going to make this just regular 6i, and then that negative sign is going to distribute across to the negative sign on 9i, and a negative times a negative is a positive, and hopefully you remember that from other courses. So there you go, you have 2i plus 5j minus 6i plus 9i. Oh, that should be j, I'm sorry. Sorry about that, guys. 9j plus 14i minus 14j. So you've got this massive mess of numbers now, but we're in a good spot actually, because now we can group them. So let's just do just that. Let's take all the i's, and I'm going to do I here, and we're going to have 2i minus 6i, and I'm just pulling these guys down. So just looking at the i's here, and you can almost circle them if you want to be extra clear about this, plus 14i, and then we're going to go ahead and do the j's in the j hat direction, so 5 plus 9 minus 14. Great. And all of this, of course, is 14j. So this means the same thing. Notice how on this one I used j, and on this one I used I kind of in each term. This is probably the more correct way, but I did this because both actually represent the same quantity. And you'll see that in a second here, because what we're going to do is we'll take 2 minus 6 is 4, and then we're, negative 4, and then we'll add 14 to that. So negative 4 plus 14 is equal to 10. 10 what? 10i. So we have 10i here, and here we're going to do the same thing. So 5 plus 9 is 14, minus 14 is 0j. And see how all the numbers end up kind of taking form here. So they mean the same thing. Between having every number in here, and then the vector, and then having the vector kind of interspersed, the same thing happens. It works both ways. So either way, you'll have 10i, 0j should be the vector that you come to. So we're going to put that down here, 10, and we don't want to use the standard basis vectors within the vector notation. So if I have the brackets, that means we can write it like this, 10 and 0, or we can write it as 10i plus 0j. And hey, if you have 0j, if it's 0 of anything, we don't actually have to include that. So it's just 10i if you're writing this in the standard basis vector form. But I like to keep things simple, and I like to have them in this like clean notation there. So this is our vector w. So now that we have w, it says calculate the magnitude of it. And as we remember before, that the magnitude is just the length of something. And so the way we take the length is if this is a and b, right, we do the square root of a squared plus b squared, because vectors can be thought of like triangles, and we're finding the hypotenuse given the legs. So given legs 10 and 0, then the hypotenuse, the length of w, and we write that like this, the magnitude of w, is equal to the square root of 10 squared plus 0 squared. 0 squared doesn't really matter, so you get the square root of 10 squared, which is equal to root 100. And if you left your answer like this, that is perfectly valid. So that is how you would look at the magnitude of a vector. And so it's not actually that hard. I hope that you can get that. We just break it down into small pieces, take your time. It's easy enough to do. So let's go ahead and do another one. This is problem number 19, and let's read this out loud really quick. Let u and v be two non-zero vectors that are non-equivalent, so they don't equal each other, and consider the vectors a is equal to, it's made up of 4u and 5v. So we don't know x and y, but we know that a has components of u and v in it. B is the same way. B equals u plus 2v. And again, all the vectors are defined just in u and v. And then we're going to try and find a scalar, lambda. Don't let that scare you. Basically, it's just saying let's find a number such that the vectors a plus this variable lambda b and u minus v are equivalent. So I'm going to give you another 5 seconds. Pause the video if you want to take this on your own, and then we're going to go over it. So starting in 5, 4, 3, 2, 1, and let's go ahead and take a look, guys. So first thing first, let's see. It says let u and v, right, they do not equal each other, but they're two non-zero vectors, and they're non-equivalent. That means they just don't equal each other. So we cannot say that u is equal to v. And usually when they put that kind of language in a question like that, it's because there might be a cheat way to do that. So if like you set both u and v equal to 0, then maybe you could get lambda equals 1 because 0 plus 0 is 0 minus 0, and something dumb like that. And so they usually write that language to prevent students from finding like the lazy way to do something. So that's all that is. Don't let it confuse you. Non-equivalent isn't that important. It just means u cannot equal v. But we have u, which is some vector, and the way you typically, if you don't know what the vector's components are, you usually write it like this, u1, u2, and all we're saying here, this is because we might extend a vector into multiple dimensions, right? You might have a 3-dimensional vector, and if you did, of course, that'd be u3 here. And this is just saying the same thing, right? This is saying the same language as ux and uy, but sometimes you just might see it written out like this, and don't let that scare you. It just means we don't know the components of u, but they're there, and we want to just understand that they are there, right? So this might help you to just picture things better. So we have two vectors. We have u and v. We know that. And we also have two vectors that are defined a little bit more explicitly, right? We have a vector a, and I'm going to do this in blue. A is equal to 4u plus 5v. And I have another vector b, and b looks like is equal to u plus 2v. And remember, those arrows on top tell us that we're dealing with vectors here. So b is equal to u plus 2v, a is equal to 4u plus 5v. And we're defining these in terms of u and v. So it says find the scalar lambda, which again is just some number, right? And we use the Greek letter because I guess we want to make people more confused. But that's all that is. So don't get your head in a twist over it. It's all good. Find the scalar lambda such that vectors a plus lambda b right? A plus some scale factor, some scalar of that vector triangle, such that vectors A plus lambda B and U minus V are equivalent. So A plus lambda B equals U minus V. Now, one thing that's really cool about this problem that I see immediately is we don't actually ever deal with direct components of U and V. The problem never asks us, like, is equal to UX plus Vy or something weird like that. We never hear that. And so because we're only talking about U and V, I think the best way to think about this problem for you, especially if you're starting out and still working with vectors and learning about them, is treat these, just imagine in your head, take a partition in your head, and I want you to imagine that U and V are just regular old variables from single variable calc, just normal variables. They could be whatever. They almost don't matter, okay? And I want to do that so that we can focus on what we're going to do next. And if we think about these in variables, we remove that abstraction layer of vectors, then this problem is going to get a lot more simple. So let's go ahead and substitute in A and B for A and B here. So this equation up here is going to equal 4u plus 5v, okay, and remember that's just A, plus some lambda times u plus 2v. And I'm still putting the arrows on top because I want to make it clear notationally. These are still vectors, but we're going to think about them like variables, okay? And that's still equal to u minus v. So let's break this down. Now, notice that we're describing A in terms of U and V, okay? And so this is one thing that's really cool about vectors is we often talk about their components in terms of X and Y, right? But we don't necessarily need to. And so you might end up with a vector where, and you'll rarely see people ever use this notationally because it's not right. But hypothetically, if we had a coordinate system that looked a bit more like this, right? And this gets into like transformations of coordinate systems and, probably very, very basic level linear algebra type stuff. But if we have a coordinate system that's the regular coordinate system rotated by, some, like call it 30 degrees, then this might be U and this might be V. And we are now talking about a vector whose 4u, 1, 2, 3, 4, 5v might look something like this. And that very well could happen to be described in the regular x and y. So the key point to understand here is, the reason I'm kind of saying this is that if we imagine these as variables and also as kind of unit vectors in their own direction, so instead of the direction x, right, which is I, right, if I had 4i, you know that means we're going to go 1, 2, 3, 4 along the x-axis. Well, now we're going to go 1, 2, 3, 4 along the u-axis, and it could be this way, it could be that way, we don't know. And it doesn't really matter that we don't know, because what we can do is group what we do know, and we don't actually need to know the exact value of u or v for this problem. So let's group, and I'll show you what we're doing here. First, we're going to distribute this lambda, so this is going to be equal to, and remember, scalars work just like any other thing, so we're going to scale the legs of our triangle here. So lambda times all of this is going to equal lambda u plus 2 lambda v. Now I just wrote that a little cleaner, but all I'm doing is lambda times this term too. So just like a triangle, it's just a big triangle. I'm going to put this up here. Oop. There's my tool. Nice. Okay, and then we're going to kind of group everything together. So let's highlight the u terms. I'm going to remove these brackets now that we've kind of cleaned everything up. And so we have 4u and lambda u. Then we've got a u on this side of the equation, right? Then we also have a 5v, 2 lambda v, and a negative v over there. Pay attention to that, right? This is the best way to think about this. Is let's think about this equation as 1u minus 1v, or plus negative 1v. And if you think about things like that, it's going to become pretty clear what we're about to do. So what we're going to do is, looking at the u's first, we're going to have 4u plus lambda u is equal to 1u. And this should be super quick for you. You should see this and go, oh, 4 plus lambda. Gee, well, what would be 4 plus lambda equals 1? And that answer is, of course, negative 3. So if lambda was negative 3, this is 4 minus 3, which is 1. So we say lambda is equal to negative 3. Now, because lambda is a single number that scales, right? It's here lambda b, and then it scales both legs of the triangle. This lambda here needs to be the same lambda as this by definition. It's the same number. So what this means is that if we're right about lambda being negative 3 should work for the v's. So let's do the v's. So the v's, we're going to have 5v plus 2 lambda 1v, right? That's a single v there. So 2 lambda v is equal to negative 1v. And in what situation? Well, if we plug in 2 times negative 3 up here, 2 times negative 3, that's going to be negative 6, right? So 5 plus negative 6. That's 5 minus 6. And as we all know, 5 minus 6 is negative 1. So again, lambda is equal to negative 3. So that means what we've done here works, and lambda is indeed the scalar that we need, and it's going to be negative 3. And there you have it. Okay, so let's just do a couple more here. I think I only have, we'll see. If we can get this all in before 35 minutes, we'll do 45, but otherwise we'll call it there. Consider the vector a of t is equal to cosine t with components, cosine t sine of t, excuse me, with components that depend on a real number t. So that means as t is changing, right, these will actively change. Now we call this a vector valued function. You'll learn more as you continue in your calculus course. But what you need to know right now is that t can be whatever we want it to be, and it's kind of cool because we have a function now that describes a variable, or that describes a vector through time. Usually when we see t, we're talking about time. Not always, but it can help you to kind of visualize what we're doing with this vector here. So it says a of t is equal to cosine t sine of t. And as the number t varies, the components of a and t change as well, right? So depending on the functions that define them, we're going to write, the first part here is write the vectors a of 0 and a of pi. So again, I'll give you 5 seconds to think about this. 1, 2, 3, 4, 5, and off we go. So the vectors a of 0 and a of pi are super simple, right? That's our t. So if a of t is equal to 0, then that means we're going to have a is equal to cosine 0 sine 0, just like a function. Totally normal, totally regular, super duper simple. And this is just unit circle stuff, right? So you can plug this into your calculator if you want, or you can just think about a unit circle and say, well, if I start at 0, right, this is 0 in our angle system here, then cosine of 0 is equal to 1, because we're moving on the x-axis, and how tall is this angle 0? It's not tall at all, so it's 0, and so sine of 0 is 0. So a is equal to negative 1, 0 for a of 0. That's all we're saying there is a of t equals 0 is going to be that vector. And a different vector, see, it's just like a function, you guys. It's super duper simple, just like a regular function. A of pi is going to be, let's think about pi here. So if we have pi, 2 pi, right, this is our unit circle. It has 2 pi radians total, and this is pi over here. Then our cosine of pi will be not 1, but negative 1. Right, we're not going this way, we're going this way, so negative 1. And how tall is pi angles? Well, it's still 0, so negative 1, 0 on the unit circle. Pull the unit circle up or just use your calculator. Either or will do it. So we've done problem A. We've given the vectors in this form where we've plugged in a number for t and got the work for it. So that's the first bit there. Now we're going to do the second bit, and it says, I'm going to kind of clean this up super quick. It says, show that the magnitude of A of vector a of t remains constant for any real number t. Cool, so I'm going to move this up here. Don't let that scare you. Anytime, here's the really cool part about math. Anytime they say show that blank is something for every blank, and they say for any real number, and then they give you a variable, this is just an instruction set that says plug in this case t, plug in t. That's all we're saying there. And so if we plug in t, right, then any real number that we could have is described in the general case of a variable. I'll show you what I'm saying in a second, but all I'm saying is that this is normal. This is super duper simple. So let's do it. For b, right, we will have the magnitude a of t. Well, what is the magnitude? And remember that magnitude like this and magnitude like this mean the same thing. Sometimes you just see them written differently. So the magnitude of a of t, just like we've been doing now, is it's going to be the x component of a squared plus y squared. And we're not going to use these brackets. We're actually going to do a big old square root, right? Because we're treating this like a big triangle. And so we're using the Pythagorean theorem. So that means that the magnitude of a of t is going to be equal to the square root, and I like to do square roots like this, the square root of, what's that first x component? It's cosine squared t, plus, what's the y component? Sine squared t. And there you have it. So this is the magnitude function that we've been so used to using. Now the reason they say it's constant for any real number t is, hey, what do you know? If you remember your trig well, then you know that cosine squared t and sine squared t is just equal to 1. So no matter what we do, a of t is equal to 1. And what's a really cool check we can do to confirm this? Well, we can think about the fact that cosine t sine of t, we were using our unit circle. And as you remember, with the unit circle, the radius is always 1. So this logically tracks, which is always a very nice thing to have. And hey, really quick, just a side note, if cosine squared t and sine squared t didn't immediately make sense to you, I just want you to know that's okay. You will learn as you go, and this will become second nature given enough time. I just want you to know that you're in good hands, okay? So let's do C really quick. And it says, as t varies, show that the terminal point of vector a of t describes a circle centered at the origin of radius 1. And funny enough, we just ended up doing that in our little proof here. And so the way we would write this is that t is equal to angles on the unit circle. And then I would show this by just using two examples. So you might say that for theta is equal to, I don't know, let's say pi over 2, which is this angle here. Cosine of theta is equal to 0, and sine of theta is equal to 1. And, right, if I did a of pi over 2, then you're going to get the exact same numbers. So you're going to get 1. Did that again, I'm sorry. You're going to get 0 for the x-axis, right? X is 0 here, and 1 for the y-axis. And so that shows that, hey, look at that. Cosine theta, sine of theta, it matches with our vector here. So that is always a very, very good sign. So we've just shown that as well. Don't read too much into this. Showing just, means give me some explanation, and it's usually pretty open-ended. You just have to convince someone of what you're saying. All right, two more, guys. I think we can do it. So 45, that's the problem number here. Check this in the textbook if you want to do these as well with me. I'll give you 5 seconds. 1, 2, 3, 4, 5. And let's get into it. The speed of an object is the magnitude of its related velocity vector. A football is thrown by a quarterback that has an initial speed of 70 miles an hour and an angle of elevation of 30 degrees. Let's go ahead and write that in here. 30 degrees. Determine then the velocity vector, try and make that straight, the velocity vector in miles per hour, and express it in component form. All right, so let's think about this. If we're throwing it and it has an initial speed of 70 miles an hour, right? What we're saying here is if we're only given the speed, I want you to think about this. Speed is what? Speed is the magnitude of velocity. And how do we calculate the magnitude of a vector? We do the square root of component 1 squared plus component 2 squared, okay? And there's two components in this. If this is our triangle, and I love to think about vectors as triangles, and you'll see why here. This is our triangle, and we have 70 here as the hypotenuse. And then down here, we're going to have two components, an x component and a y component. And we know the angle between everything, we know the angle in this triangle is 30, then we've actually just set up a very, very basic trigonometry problem. So the vector then is going to be described as the component of x and y. So we would have 70 times the sine of 30 being the y-axis here, right? Because remember, x is, whenever we have an angle that's centered horizontally like this, like it's measured with respect to the horizontal axis, then cosine describes x and sine of the angle describes y. So 70 sine 30 is y, and 70 cosine 30 is x, and these are the components. So I would do two things. It says we can determine the velocity vector, but it wants it in miles per hour, and typically you don't say 70 sine 30 miles per hour, and so what we would do is give you an actual number for that. And so let's do it. The number, and make sure your calculator is in radians, because that might, or excuse me, make sure your calculator is in degrees and not in radians, because that might get you just a bit of warning there. Let's do 70 sine 30 though. 70 sine 30, now that's the y-axis, okay? 70 sine 30 is 35, and 70 cosine 30 is 60.62. 60.62. So I did these kind of backwards. I did y first and then x. It doesn't really matter. You just want to make sure no matter what you do, your vector is always in the form of x naught, y naught, or x and y, right? We never want to do a vector as y directions, x directions, because that's just confusing for everybody. It's just like a point, right? A point is always the x direction and then the y direction. Well, vectors are the exact same. So our vector should be 60.62 comma 35, and if you wanted to express it with standard basis vectors, that's also the same as 60.62 I plus 35, say it with me guys, 35j. Very nice, and I think we're just on time here, so I'm going to do one more, and this is 46, and then we're going to call it a day. Like I said, if you've done all of these and you feel confident about it, you're going to be in a good spot going into the rest of your vector calc course. So let's go ahead and do it. A 65-kilogram sprinter exerts a force of 798 newtons at a 19-degree angle with respect to the ground. So that means 19 degrees respect to horizontal on the starting block at the instant a race begins. It's time equals 0. I'm just putting down what I think out loud here. Find the horizontal component of the force. So let's figure this out. And if you're a mechanical engineer like myself, you're going to be using this a lot in later classes. So it's always good to know. So round to 2 decimal places. Good to know. Let's see. A 65-kilogram sprinter. Honestly, that doesn't really matter. It might matter. Yeah, it might matter. So let's see. Yeah, because that would be their normal force. That's just side level stuff. Don't worry too much about that. 65-kilogram sprinter exerts a force of 798 newtons at 19 degrees. What's really cool is that this ruler will give me that exact measurement here. It doesn't need to be exact, but I think it looks prettier when it's nice. 19 degrees, and this force F is equal to 798 newtons. All I'm drawing here is a picture of what's going on. That's all it is, a picture of everything that's going on here. And it says find the horizontal component of the force. And if you think about it, right, as you're a person, you're going to be doing two things when you're running. You're going to be pushing up to keep yourself moving upwards and not falling down, and you're going to be pushing forwards so that you actually go where you're looking and where you want to go. So we're talking about the forwards force that we're pushing here, the horizontal component of that force. And if your intuition is right here, because we've always been talking about these vectors as triangles and the components as triangles, and we have an x and y here, and remember what we said, for 19 degrees, what would be the component here? And we said that it's always the cosine, right? So cosine of 19 degrees times the hypotenuse, 798. And just for good measure, you can do the same for y too, 798 sine of 19. So there we have it, 798 cosine 19, and let's do that. 798 cosine 19 is 798 cosine 19. You should get 754.52 newtons. And this is a great little check too, because this actually makes sense, right? If we have someone who's trying to run forwards, most of the push should be in this direction, right? If you push too much up, you're just going to end up jumping instead of running. So we want to run and not jump, so the x component should be big and take up most of that 798. Now, if you want one further check to make sure what you did was right too, you can also remember that, like any triangle, a squared plus b squared is equal to c squared, for any right triangle I should say, and all vectors are right triangles. And so we can also do 700. We can do 798 sine squared 19, or I guess 798 sine 19 squared, plus 798 cosine 19 squared. And if we took the magnitude of this vector and we said the square root of 798 sine 19 squared plus 798 cosine 19 squared, this will end up equaling 798, which is the length, the scalar quantity magnitude of that force, which means, hey, we did it. It worked. And I think that's all for us. That's a nice long video for you guys. So if you were able to get through all of these, you feel good about it, then you're in a good spot. And yeah, you got this, guys. I'll see you in the next video.